All right, so yeah, hope you all are having a fun time here in Portland, not Portland. I know that this has been well, I don't know, I've been to a lot of hackathons now, and security is always one of those things that comes after you do the hackathon project. But more and more, we're seeing that get pushed back up until a launch date, and then an audit, and then a lot of unanswered questions around things that you could have potentially built for in the very beginning. So even though I'm sure many of you are not going to be rushing out to get an audit after you do your hackathon projects, I think a lot of what we're going to share here today might be interesting. Tales of woe, how not to do it, those are always useful lessons to have in the beginning. So let's start first with just a quick overview of the agenda. I'll talk a little bit about what Open Zeppelin does. Some of you are probably very familiar, but sometimes people haven't heard about everything that we're up to, so I'll share a little bit about that. And then I'll just go into some fun security case studies. What are some really bad accidents that have occurred? What happened? How did we learn from it? What are we now doing to prevent it? And then go into just a bit of a summary and Q&A if we get the time. So let's hop right into it. First of all, Open Zeppelin. What do we do? Our mission is to protect the open economy. I think if you want to hear a little bit about where that came from, some of the original founders of the team are actually from Argentina. And if you didn't know, it's not the best place to hold a currency or work with the government or things like that. So having an open economy, having accessibility for people, having this sort of economic freedom is at the core of it. But you need to have an economic system that is secure in order for that freedom to also be secure. Hence, we work on security audits and build security products, working with many of the fine clients that you see here. UMA is here, by the way. We love working with them, and many others. So how do we do this? We have three main pillars of doing security in the industry. You probably have all heard of Open Zeppelin contracts. That's very common in a lot of projects that people are using. It just basically builds out nice standards. We'll talk more about that later. We also do a lot of audits. We have a security team that basically tries to break your code for you and then tell you how to fix it. And then finally, we build products such as Defender, and we actually have someone from the Defender team, Ernesto, who will be talking more about that after me. So with all that, let's talk a little bit more about history, because I am a fan of history, and there's a lot of history to talk about. So first of all, the DAO hack, the first big ouch, the first splash of cold water to building on an immutable secure blockchain does not mean the code is in itself inherently secure. So what happened? So really, what we saw with the DAO was an early set of smart contracts built for crowdfunding Ethereum development projects. We all call it the DAO because it was the first DAO. Sometimes it gets very confusing for people that have heard of the DAO hack but not other DAOs to know when you're saying a DAO, it's not just this thing. But so we say the DAO. And it was a hack that resulted in the loss of 11.5 million Ether, which was about 50 million at the time. If you want to do the math on how much that is today, it's a lot. And ultimately, the way this occurred is an attacker exploited multiple vulnerabilities, but most especially a reentrancy bug, that allowed them to recursively call the send function before balances were updated. So you can see an example of that on the screen. You can see how it basically just turned into a recursive call. Well, I wouldn't say recursive is the right word, but basically, you go through the process. You're calling to whatever you're sending that value, and if that thing you're calling to is a contract, and you don't have reentrancy protection in place, it can just then come back, recall that contract, and you never hit that bottom line where the balances are going to be decremented, so you just continue to withdraw funds you don't technically have a right to until you essentially bleed it dry, and that's essentially what happened to the DAO. This was bad for many reasons, but most especially because it prompted a community hard fork, the only hard fork for Ethereum in terms of basically like kind of one time only breaking this immutability rule of transactions are final and saying this one, this is our first and hopefully only mistake. And it led to a contentious split. We now have Ethereum Classic as a result, where the DAO funds were never returned to the original users. And yeah, there's a lot of I would say, issues that came from this. So when we look at the takeaways and we think about, OK, what happened here? Smart contract developers, first of all, are going to have to account for malicious calls from external contracts in accounts. So just because your contract, you might expect it to talk to users in certain ways, but you have to realize this is on a public blockchain. It's not like a Web 2 server where you're sitting in a server, you have a large firewall around it. You can kind of usually have pretty strong assumptions about who's calling it and who can. With a smart contract, anyone can call it. Anyone can show up, start poking it, and figure out a way to break it. So you have to be very adversarial thinking about how people are going to call your system, and even in ways that you might not expect. You're also going to be you have to be aware of your state and balances of a contract. If you are sending funds or doing some external call, you might want to update state prior to that in case that call is going to try to do something before you can update the state afterwards. That was a key part of how this happened. So just the basic practice of decrementing a balance before you actually send the money is like one core way to do that. Also, forking a protocol. To reverse attacks, it's possible. It's kind of technically an option, but it also heavily damages the community and the platform's reputation for censorship resistance. Ethereum has come back from this. Like, we're at the point where we've had many worse hacks that we'll talk about in a second that has not resulted in another hard fork. But this is if I live in Texas, so I talk to a lot of Bitcoiners, and every once in a while this does come up. And like, out of all the critiques that Bitcoiners might have about Ethereum, this is the one that does have a little bit of difficulty in justifying. Like, yeah, we did have this exception case. There was a time where the community decided to do a hard fork and reverse funds, and there's a question of will it ever happen again, and will it happen for the right reasons. So far, it's kind of become a one and done for Ethereum, but nevertheless, it's not an option you really want to see on the table going forward, and so the best way to prevent that is just to make sure there's never an attack so bad that it ever feels like an option you even have to consider. And in general, having better security standards, more secure Solidity implementations, that's what's needed to prevent these sorts of exploits, because not everyone can think through all the potential ways that a smart contract can be hacked. Sometimes it's better to just use what's already there. So one of the things that's already there are open Zeppelin contracts. So some of you might have already been using our contracts. We're probably most famous for our token standards. We take what the existing token standards like ERC20, 721, 1155, and we basically implement it in our contracts in a composable and extendable way. So in addition to being able to just take these very easy to use templates, putting in your parameters like your token name, your symbol, your amount, you can also add extensions to this. You can say, I want it to be a pausable contract. I want it to be a mintable contract. I want to do snapshots, all these other things. There's actually a thing called a contract wizard that lets you just literally put in those parameters and say, this is what I want. It'll spit out a contract template for you to start with, and then you can go from there. We can also do, we have a lot of upgradability systems that are very nice. If you want to upgrade your contracts, we have a lot of systems to do that, including plugins. We have access controls, so you can do an ownable contract. You can do role-based permissions. We have utilities for cryptography, math, create to data structures, and then governance, which is a new thing that we ported over from Compound Governor Bravo, so you can do governance as well. And then finally, most importantly, for things that are important for the DAO hack is we have security modules, things to prevent exactly that from happening with a reentrancy guard and pull payments. So very quickly, how do those work? Well, with reentrancy guard, basically all it does is it's just a modifier. It's a modifier you put on top of a Solidity function that says, we will basically prevent this from doing any sort of reentrancy. I will say this isn't like an ideal solution for everything. You don't want to, because it does cost gas to use, but like if you're in a place where you're just not sure what's going on, you don't want there's a possibility of reentrancy that you just don't know how to mitigate against, this is like a good, just one and done option to prevent that from being possible. There are scenarios outside of just wanting to be more gas efficient where reentrancy guard might not be a good idea, such as a payment system. You do actually need to do external calls or do something that opens the possibility of reentrancy up to do that. But there's actually other ways you can do payments. Like the typical way that the DAO was doing it and others still do it today is that you have a function that then sends a payment out to an escrow, which is kind of the push payment model. In a lot of those cases, we'd actually recommend a pull payment model, which essentially means that instead of having someone do a push payment and send it out, you would actually just have that function within the smart contract delegate funds out to that escrow contract to say there's going to be these funds, we're just going to set it over here, and anyone can pull it out. And then from there, the contract or the user can then withdraw it, pay for their own gas, and then get that payment out to them. So it becomes a two-step model as opposed to a one-step. Maybe you like that, maybe you don't, but in any case, it does remove the possibility for reentrancy to cause issues. So that was one. I'll do a second. The Parity Multisig hack. No one is perfect. So with the Parity Multisig hack, what we had happen was essentially a core library that everyone was using, the Multisig library contract that at the time, Parity was running a node. They had a Multisig wallet that came with it that was built as a smart contract. And a lot of projects were using this to store their funds. And what happened is essentially there was a way that they were using the Solidity library, which is not, or Solidity library functionality, which is actually, I don't think it's very common nowadays, primarily because this hack kind of opened it up to a lot of flaws. But the idea being, you don't want to have to redeploy existing code to the chain over and over again. Why don't you just deploy the core logic for something that everyone's going to use, and then everyone can just call out to that as a dependency, and you could save on gas, and you can also make sure that you're using the right implementation. However, if that core logic does have issues, especially the way that dependencies are using with it, or essentially interacting with it, there are flaws that could come up. So what happened is essentially an attacker found a flaw, was able to steal over 150K worth of ETH, which is about 30 million at the time. Also do the math now if you want to know. And then they got it from 3 high-profile multisig contracts from their token sales. And so the attacker was able to obtain this exclusive ownership over those funds by calling an initializer function inside the library using delegate call. So delegate call comes in, which is something you also have to be careful about. And so other wallet funds later, like after this whole thing this hack occurred, there was also an issue where there was an unintentional self-destruction when they were trying to actually do some upgrades related to this hack that left another $150 million actually locked up that no one could get to. So yeah, this did not go very well for Parity. In fact, there was even calls for a potential hard fork that didn't go anywhere, but it was that bad. So the breakdown of the attack, very simply, was just the fact that the attacker found this fallback function, where it was automatically payable. And the idea of this fallback function is that you're going to take in either a deposit. A fallback function could just be a payment that's being sent to the contract. And basically what it's doing is it's saying, OK, if I'm getting value that's above 0, as in I have a payment, I'm going to treat this like a deposit event, and then be done. Else, if this is containing some sort of a data, as in it's maybe doing a function call, I don't know what this is. So this is like the multisig contract, the implementation that someone's deployed for their project. What was built into it is to say, hey, if I don't know what this is, I'm going to delegate call, as in I'm going to give this to the library contract, and I'm going to let the library contract figure out what to do with it. Well, the problem with this is that with that functionality, when you call init wallet and you give it the attacker's address, you would actually see it go into the init wallet, and then it would basically initialize the wallet. And by initialize the wallet, it means it sets the owner. So what you do is you're reinitializing the wallet more than once after it's already been initialized as an attacker, and then saying, oh, and this is the owner. And that basically becomes me if I'm the attacker. So it was just functionality that was not clear, because delegate call was kind of this open-ended thing of like you can just pass anything to it. And so they were thinking the only time someone would call the library contract for init wallet was when they were creating a wallet, not realizing you could call init wallet on that same wallet after the fact. So ultimately, yeah, this led to a lot of bad results, lots of funds lost. So what was learned? Well, first of all, anyone can fail or anyone can screw up. So Parity was founded by Gavin Wood, the former CTO of Ethereum and creator of Solidity. If anyone knows how the EVM works, it's him. And still, even though he wasn't maybe directly involved in the code, we know that there's like discussions about how much did he look at the pull requests, et cetera. Like, it's his company. If there's any company that you think would be infallible, it would be him, and clearly it's not that case. So even the most reputable developers can make mistakes. Also, we learned that functions defaulting to public visibility, as this did. So when you look at that, you notice that there's no visibility on that function. It just says, on either init wallet or the function call, and it just says, can people call it from different dependencies? Should it only be called directly, externally, or can it also be called internally? It wasn't clear. And Solidity just, if you didn't tell it which one, it just defaulted to, I guess it's public, which means that you also open up the potential for these exploits to occur. So this is why now Solidity version 0.5 requires explicit visibility. You have to actually say and at least think about what you're doing with it, which also means don't just put public on everything explicitly. Still think through, why am I giving this visibility? Think through that a little bit. Complexity involved with using libraries is also a takeaway. Like, there's just delegate call, even if it gives you some very useful things to do, some very open-ended ideas, it also potentially presents a security risk. And even simpler code might be better than saving gas fees, which is a long-running debate as gas fees increase, especially today. This is something that I think we're going to continue to see. But I think for us at OpenZeppelin, we usually see this as principle for writing code. If we can, maybe we have to pay a little bit more gas, but if we're saving people from potential security screw-ups, we think that's worth it, especially as L2s become hopefully the future, where we don't have to over-complicate our code to save on gas. Preferably, we keep it clean, and we can let the layer 2s do their job. Another thing is that there was no bug bounty program at the time to incentivize the reporting of critical issues. We don't know if that would have stopped it. Maybe even if it was a generous bug bounty program, he might have still done the attack. But honestly, the question's always there. And any attack that occurs when there wasn't a bug bounty program also has that same question. So ultimately, if you're putting out code that is handling millions of dollars, definitely consider a bug bounty program, because that's essential to catching live issues and to incentivize people to either go out there and try to find and catch it for you, or for attackers or just someone who could be an attacker to at least have the option to say, maybe I can make a little less money but clean money just reporting this issue. And then finally, the multisig wallet was audited. at one point, but there had been changes since that audit. And so we don't know exactly how this worked out, but it looked like those changes could have reintroduced the issue before the attack. It's also unclear which commit had been audited, so the way that the Git log was being set up, it wasn't clear at what point of the version was that audited and at what version was it kind of like a different version than that. So really, recurring audits with very clear Git logs are paramount. This is something we do with a lot of our clients. When we do an initial audit of their code base, we also, if we can get the time on our schedule, we try to also get follow-ups where we go through their pull requests on the code we already audited to see if that has made any impact, it has reintroduced bugs. We really want to catch those. And if you can't do it with us, do it with anyone you can. So in case you didn't know, we do audits, and the process is typically we get in the code, we do an audit, we schedule it if we can have time. Unfortunately, we're all limited in terms of manpower. And then we do fixes and then publish the results for the community to review. And we work with a lot of the major projects out there, and we see that there's a lot of stuff that we can catch prior to it going to production. But security audits are just one of many ways to do this. Ultimately, you need to do quality assurance outside of an audit. There's only so many auditors that exist in the world. Trust me, we try to hire more. It's not easy. So ultimately, you can really improve this process, even though I would always say you should try to get an audit. Even before the audit, you should be doing a lot to improve the quality of your code. Again, you're all hacking here, so I'm not telling you should have to do all these things before your project can be judged as good. But you should scale your security over time as you start getting closer to potentially launching something. So having a good Git workflow with a transparent log so you know what's being changed by who, having NatSpec comments to explain what you are expecting people to do with the code, especially if it's something that's going to be externally called. Document the architecture and relevant protocols. If you're integrating with Aave, Uniswap, you need to be looking at those and seeing how that dependency impacts your project, what happens when they change their code, that sort of thing. Having an exhaustive test suite, very nice. There's lots of great testing tools out there using Hard Hat and Foundry and many other things. Using code libraries, such as Zeppelin, and not just taking Zeppelin code and copy-pasting it into your library or your repo, but hopefully using NPM and other package managers so that you don't have to worry about potentially throwing a typo in there and then screwing up the whole it's secure code thing. And then finally, do your own internal security reviews, do your own audits. Look at your code adversarially and maybe not write features for a whole week and just try to break it yourself and run your bug bounty programs regularly. So these are all things that honestly we recommend people do before an audit. We have an audit readiness guide if you're curious below. Because ultimately, auditors can look at your code and probably find really easy bugs, but you really don't want to be paying them a stupid amount, whatever they're paying per hour to do that. You want to catch that stuff yourself and then give the auditors a really clean code base that lets them then dive in and find the really nasty, hard to find stuff. That's really what you want to use auditor time for. So with that, I'll give one more, the Urine Y Die Vault exploit. This is a less known one. There's actually a lot of great examples I could pick from, but I'm going to go with this one because we worked with their team to figure out a solution to this. But mainly this was one of those flash loans beginning to really change security assumptions in the space. Flash loans are coming for your collateral if you're not careful. So first of all, I'll start with what flash loans and flash loans attacks are. Most of you are probably familiar, but I'll go through the basics anyway. Flash loans are a type of uncollateralized DeFi lending, where the liquidity is borrowed instantly and then repaid in the same transaction block. Because normally, you want collateral behind the loan on smart contracts, because it's not like your smart contract can go to your local county courthouse and say, this person didn't pay me back, give me his house. We can't do that. So you have to work with the collateral you have on chain. However, if you are trying to do a loan, that is going to be, for something like an arbitrage trade or something that is going to be done within a single block, you have this really interesting possibility that really doesn't exist anywhere else outside of a blockchain system where you can tell someone, hey, because we're within one block where a transaction can revert if it doesn't meet a certain condition, we can literally say the condition is you can borrow an amount, you can go do whatever trade you want, and then you can repay that loan within that block. And if you can't hit the repay loan part where you have to pay back the amount in full plus interest, then we'll just revert the whole transaction, and it's like the loan never happened, which is really cool. You can do some really cool things with that. It gives people access to liquidity they might not otherwise have, but it also means anyone can now become a whale. It means people that can do these loans and then find these ways that markets can be manipulated. They can actually trigger liquidations and potentially even increase the profitability of other exploits that would have otherwise potentially been unviable to do. So a good example of this was the Urine Y Die Vault. Urine Finance does a lot of cool vaults. They integrate with other protocols. So for example, Urine had a strategy for Y Die Vault on top of Curve with their 3-pool vault, liquidity pool. And so essentially what the attacker was able to do is it was he took out a flash loan, he went into the Curve market, and he was basically able to imbalance it by doing a very large trade in one direction. And then when he basically created that imbalance, he was then able to go to the Urine Y Die Vault, which was using the pricing from Curve to determine its strategy, and then make you make deposits at a very unfavorable exchange rate, get a really good discount, and then immediately do a withdrawal, and then basically rinse and repeat. And after 38 minutes, the Urine's team actually noticed this, and then was able to mitigate the attack by disabling deposits using pausing functionality they had built. Well, actually, no, it wasn't pausing functionality they had built in. It was like a hacky way to do it, but they basically were like, all right, we're pausing this thing and then stopping the attack in its tracks, because otherwise it was just like repeating on a loop by the attacker. And Urine did a pretty good disclosure on it down there. And this is like a more detailed version. You can kind of see in terms of what that process was. Do a deposit, make a withdrawal, imbalance the pool, do the deposit, and then once you do the deposit, rebalance that pool, and then make your withdrawals, make your money. And this was coming at basically at the expense of every other person in that vault. So everyone else in the vault was basically losing money in favor of the attacker. So, what can we learn from this? First of all, flash loans have changed the game. And I made this slide back a year ago when flash loans were a little bit more hip and cool. I think people are starting to see this as a standard in the industry, but nevertheless, we're now starting to see that economic vulnerabilities are just as important as logic bugs. Like the code, it can behave as expected. There was no access control failure. There was nothing like that. But because you have these economic assumptions about how markets work, you're using Oracle pricing and other things, then that can cause what essentially feels like an attack. It feels like more like a Wall Street trader kind of attack, but nevertheless, it's one that requires sophistication and an understanding of the code. And you can write the code to protect yourself against these sorts of attacks. So it's something to be aware of. So when you have dependencies on decentralized exchanges like Curve for your on-chain pricing, you have to consider the fact that flash loan attacks could be used. So consider using other third-party protocols for on-chain pricing. So either using multiple on-chain pricing oracles from multiple exchanges to reduce that possibility, using other oracles such as Chainlink. I know UMA has oracle stuff, so ultimately look and branch out your options, and if you're depending on just one source of data, really consider, can that source of data be manipulated and attacked? Another thing is that flash loans are really only viable for an attack if they can be completed in one transaction block. I will say there's a caveat to that, but in general, that usually reduces the possibility. So consider multi-block flows for sensitive functionality. Maybe that would make it so that someone couldn't do a complete flash loan attack within a single block if you have a multi-block flow. But that's going to be slower. It's not great for user experience. So it's not the best solution, just something to consider. And the last thing that I think is really only now starting to become apparent to smart contract teams is how this was ultimately mitigated. The quick response from the Urine team, when they noticed this complex transaction pattern, just by chance, by someone just having to notice, hey, that looks weird on Etherscan, what's going on, did allow them to respond and save millions and die. So fast threat detection and response is critical for protecting user funds in this day and age. It's no longer good to just deploy something and let it go into the wild and say, you're free. Go forth. I will not worry about you anymore. You actually have to, as a developer, especially when you're building complex economic systems, keep an eye on your code and consider, what do I do if someone's attacking it? What is my plan? And how do I know someone is attacking it? So this is where other things that we have come into play. So Open Zeppelin Defender. This is a tool that we've been building for the last year or two that is specifically made for security operations. It's made for protocol teams and developers to be able to very quickly, essentially both deploy code in a clear format, being able to do processes that you can automate, so reducing the potential for manual error. We do key hosting, although you can bring your own keys. So we have both options. We'll keep your keys for you, or you can bring your own keys, or you can do a combination where you have a multisig that delegates authority to one of our keys, whatever you like. We have auto tasks, which are just basically Lambda functions with all these nice little Ethereum add-ons combined, so you can do automated code that's in response to events or in response to scheduled tasks. You have sentinels, which are going to monitor transactions and trigger notifications and auto tasks, so you can be known, when is something weird going on, when is a transaction being triggered, that sort of thing. You can get it through Discord or Slack or email or whatever your fancy is. And then we also have Advisor, which just contains some nice little security best practices in there. So Ernesto's going to tell you more about Defender in a second, but the other thing I'll throw on top, because I'll say, when you're looking at this, you're like, oh, that looks nice, but that's a SaaS product, man. That's Web 2. What are you doing? That's kind of that's old school. And I would say, well, there's still places where Web 2 makes sense. But if you are worried about potentially that being a point of failure for monitoring, you want more redundancy, you want something the community can touch and love and feel and play with, that's where the Forta network comes in. So the Forta network is a decentralized community-based security network. It's kind of like the Graph or Chainlink, but for security monitoring specifically. This is something that we've been incubating at Zeppelin because we saw this as a real pain point in the community. And we built it specifically so that anyone could go out there and say, I want to create a security agent that's going to detect certain security vulnerabilities, whether I'm part of the protocol team or I'm part of the community, or I'm just like a random guy that wants to see what's going on. You can write these code scripts. You can deploy them to scan nodes, which are anyone can run, and you stake essentially tokens to run them. We have some economic ideas thrown in. We're still in beta, so we're working out some of those. But basically, the idea is people are incentivized to run their own monitoring nodes. You have redundancy. You have a transparent way to see what's going on and look at the data yourself with our own little block explorer you can see there. So the idea is we want to decentralize security for especially monitoring, because everyone should know when their protocol is being attacked, not just the protocol team, not just people that have signed up for a Defender subscription, but everyone. So this is something that it's separate from Zeppelin, but we've been working very closely. We've been incubating it. We've been kind of working a lot with their team. And we are integrating it with Defender. So essentially, these sentinels that are triggering transactions and auto tasks can also be wired up to use Forta. And we're actually looking to do that more and more as time goes on. So how we think about smart contract security. So really what we're thinking about is there's both pre-deployment and post-deployment. Pre-deployment, I think people have been talking about for a long time. We've been talking about reusable code libraries and templates and ways to prevent people from rewriting code that should already just be considered a secure standard. Having testing, having documentation, and of course getting audits prior to deployment. But more and more we're seeing that post-deployment is just as important. We need to have, first of all, bug bounties so that as code is live and vulnerabilities come up, there's incentives for people to report that directly to the people that can do something about it. We want to have real-time monitoring, which is what Forta comes in, and we also want incidents and emergency response operations, which, again, you can do all of these on your own, but Defender tries to build these tools to be very quick and accessible. So in summary, the DAO hack, what did that learn? We learned that simple modular contract code with Ethereum security in mind is ideal. This is me shilling opens up in contracts, but that was a good example for why you want to use existing standards. Not just us, use Genosis Safe, use other things that people have already built and they work really well and they're already securing millions and billions of dollars. Use that instead of implementing it yourself, And Parity Multisig hack, we learned that bug bounties, internal QA processes, all of these are really essential for keeping smart contracts secure. And then finally, the Y Die Vault issue, as well as all the other attacks you see using flash loans and other weird economic vulnerabilities. Operational security and real-time threat monitoring is critical. You can't just put it out there and say, it's free. You need to protect it. You need to be ready to do upgrades, respond quickly. Whether you're doing that or you have someone else in the community doing that or the community as a whole figures out how to do it in a decentralized way, it's still an open question for how you do that, but it needs to still be done. So there needs to be a plan and thought process in place. So ultimately, the attack surface for smart contracts is continue to grow exponentially. We haven't even talked about bridges. I think QuantStamp will talk about that later. I'm looking forward to that talk. But in general, practice good security both before and after deployment. Even when you're in the early stages, you just want to be thinking about these sorts of things. And always stay safe. So I don't know how much time I have. If you want to look at some resources that I mentioned, I've got plenty there. Where are we at time? I don't know who has a clock, or I guess I can look at my own phone. Oh, wow, 10:29. I have time for one question. All right, go ahead.
Hi, thanks for your presentation. My question is just, do you have any rules of the road for people looking to evaluate the security of bridges and some of these cross-chain smart contracts? As multi-chain becomes more of a thesis, I think given hacks and Roman and other kind of, chain code applications specific or VDM in general, how do you think about bridge security? What are ways to look at that?
Gotcha. So yeah, for people that didn't hear it, basically, how do we think about bridge security? What are rules for the road? What are our thought process with that becoming a more common thing? I will say it's a developing field. It's something where I wouldn't say there's not any set rules because it's just changing so much, and the type of bridge that you're working with could be very different depending on how it's implemented. But I would say there's a lot of more points of attack than you have with normal smart contracts. You have to consider, two networks. For example, if you look at Wormhole, which was the big Solana bridge attack, you have to worry about smart contracts on Ethereum. You have to worry about smart contracts on Solana. In that case, they're not. Solana is not even EVM compatible, so it's a very different framework. And then you have to worry about the cryptography and the bridge network between them. You have how many bridge nodes are running. What is the power of a bridge node versus what has to be verified on chain on both sides. And then, of course, just the fact that there's so many issues that could come up with that. In that case, it was just like, something didn't get updated. Something was deprecated on Solana. It was actually a known issue, but they hadn't fixed it. In fact, I think they actually had to fix in a PR request. They hadn't deployed it yet. And there's an open question of, did the attacker see that PR and say, wonder what's that fixing? Let me look into that. We don't know that for sure. We can't interview the attacker. But I will say that, I think bridges are a very important security point. I mean, if you're building a DeFi project and you're using a stable coin or something that's actually coming through a bridge from another protocol, like Terra, UST, or other things like that, you have to really think through, okay, what is my sensitivity to bridging? You also have to think about that for L2s. L2s should be more secure because you do this, you have this ability to exit. But even then, you have to think, what happens if the sequencer goes down? What happens if the issues? There's a great thing called L2 Pulse or something. Say again? L2B, yes, that's a good one. They actually have a really good section where they go through what are the security risks of this L2? Do they actually have fraud proofs? Are they upgradable? So that's a good resource to look at if you want to learn it. But I will say it's in flux. There's a lot to still be learned about bridge security, and hopefully we will not make too many mistakes learning it. So I think that's all the time I've got. So I'm going to hand it over to Ernesto, and he'll take it away. So thank you, everyone.